Welcome back to the neighborhood and to Permu's balcony, where we left off yesterday. This is the second part of our talk on permutations and combinations. If you haven't seen the first part, go back and check that out first, because we're going to pick right up where we left off from yesterday. So if you remember, combine had combinations, and there was something very important about these 6 arrangements of the flowers that I wanted to talk about. Just want you to listen very closely to what I have to say, because hopefully this will help you make a distinction that's important later. These are 6 different permutations because the order matters. So for instance, A is in the same place here for both of these, but B and C are in different orders. So these are different permutations. If I have 3 items, I have 6 different permutations because the order matters. All of these, however, are only one combination because the order doesn't matter. These are all still A, B, and C, no matter how I've arranged them. So these are all combinations, not permutations. And if you remember yesterday when we were figuring out the combinations, what we did was we figured the permutations and then we divided by the number of duplicates that are combinations. So let's return real quickly to Permu's 5 flowers. Remember, she has A, B, C, D, and E. 5 different colors, plants that she likes. And we talked about the way to arrange them yesterday, the way she likes, where order does matter. And so when we looked at what could go in each pot, the first pot had 5. And then the second pot had 4 because we'd already used 1. And the third pot had 3 possibilities. And the fourth pot had 2, and the 5th pot had 1. And we said that this became 5 times 4, 20, times 3, 60, times 2, 120, times 1, 120 permutations. Now, we'd like to write this in a notation for math, because mathematicians like to have a more convenient way of writing things than just like this. And so it's kind of interesting because I think this is surprising. 5 times 4 times 3 times 2 times 1. And what sort of symbol do you think you would use for surprise? Well, I think the exclamation point is probably the symbol that you'd use for surprise. So if I want to talk about the way these numbers are written, I would say that this is 5 factorial. And this exclamation point here is read factorial. Why this word factorial? Well, factors are 2 things you multiply to get another, and all of these numbers are multiplied times each other. So this is factorial, and it starts at 5, so it's 5 factorial, and that's equal to 5 times 4 times 3 times 2 times 1. So can you imagine very quickly what 3 factorial must be equal to? I'll let you take a second to pause if you want to. 3 factorial is equal to 3 times 2 times 1. What would 6 factorial be? Again, we're going to start with our number. 6 times 5 times 4 times 3 times 2 times 1. And you can see as the numbers get big like this, it's really important to have a simple symbol that helps us talk about what we're doing here. How big is this? Well, we knew this was 120. So if I asked you to do 6 factorial, you could say 6 times 5 times 4 times 3 times 2 times 1. But it's simpler to just realize that 6 factorial is only different from 5 because it has a 6 that it's multiplying. So I could take my 120 times 6, and I'll get 720 for 6 factorial. Let me rewrite these real quick. So 5 times 4 times 3 times 2 times 1 is 5 factorial, and that's 120 permutations. And if I want to talk about this just in terms of the permutations, then I'm going to say this is capital P, which is not the same as probability, which would have parentheses. Capital P for the number 5, and that's 5 factorial. So the number of permutations that I can make with 5 different objects, like our plants here, is P of 5 factorial. Now what about the case of her daughter, Permu to Permu, yesterday? Now she only had 3 pots, if you remember, and that was 5 chances in the first pot, 4 options in the second pot, and 3 choices in the third, and then she ran out. Well, how can we write this? I need to find some convenient way of saying that I'm not going to multiply times these last 2 because they're not there. So why don't you take a moment and see if you can figure a way to do this, and then we'll come back and talk. So as I'm looking at this, I would like to find a convenient way to do it, and I know how to write the permutations for 5 things here. P of 5. What if I went ahead and did P of 5, but I divided it by these 2 that I'm not going to use? Would that give me what I want? The 2's will divide out, they'll be 1, and the 1's will divide out, and that'll leave me with 5 times 4 times 3, which is what I want. And then what I'd like to notice is this is actually 2 factorial here. See how that is? So if I want to write this, I'm going to call this the permutations of 5 when I choose 3. So 5 items, I'm taking all the permutations of 5 items if I choose 3. And the way I'm going to write that is 5 factorial. I could write 2 factorial, but what I'd like to realize is there is a connection to this 3 here. 5 minus 3 is the 2. So I'm going to write this over 5 minus 3 factorial. So this is how I figure the difference with a little formula. And I'd hate for you to rely on the formula because the ideas from yesterday are pretty simple. But you'll see this in books, and so it's good to be able to connect it to what we learned yesterday. So if I want to do the permutations of 5 separate objects with 3 being picked, it's the number of objects factorial divided by the number of objects minus my choices factorial. What about Combine, though? Well, Combine was essentially exactly the same as his sister. Except if you remember those 3-letter combinations that we had here, these were all the permutations of 3 letters that are identical from the standpoint of combinations. And so I need to divide by that number. And that was 6, if you recall, which is 3 times 2 times 1. 3 factorial. So if I want the number of combinations of 5 items when I choose 3, it's essentially the same as the number of permutations. 5 factorial over 5 minus 3 factorial times the number of duplicate items. Okay, and that you can see clearly from this that the number of combinations is going to be far less than the number of permutations. Now, of course, when we talk about math, we don't want to talk about specific instances all the time. So I'd like to have just a general formula. But take a moment just to make sure that you do understand that 5 factorial is the number of arrangements of my 5 items that are different because the order does matter. The permutations of 5 items here, if I choose 3, is going to be smaller because there's still the same number of items, but there are only 3 places to put them. And last, The combinations are going to be even less still, because this is going to be the number of permutations divided by the number of identical duplicates. So let's see if we can take a moment and come up with a way to talk about this in general. We're going to say that n is the number of items that I have to choose from. And then if I take some smaller number, like the 3 pots instead of the 5, I'm going to call that the number of items that I choose. So if we do that, then I have the number of permutations of n items is n factorial, or n could be any number. The number of permutations of those n items if I'm picking 3. So for like example, before we had 5 was n and r was 3. This will be n factorial over n minus r factorial. And if you remember, in the one before, that was 5 minus 3. So we divided by 2. And then the last one, when I pick my choices of n items, when I choose r of them, it's the same as this number of permutations divided by the number of duplicates. And if you remember, the number of duplicates was this factorial. So that's essentially it. Like I said earlier, I hope that what you'll do is remember the ideas behind this, because if I use ideas, I can understand pretty much any of this. The formulas are great if you want to try to memorize this and later on just plug numbers in. But if we understand it first, it'll be easier to use these later on. And so we'll leave that here, and in the next edition, we'll talk about doing some examples. So have a great day, and goodbye from Permu's balcony.